Another measure that helps us to determine the effectiveness of a new diagnostic test and to find the best trade-off value other than sensitivity specificity is the ROC curve. ROC curve is also known as ROC curve. A sensitivity and specificity of diagnostic test depends on more than just the quality of the test. They also depends on the definition of what constitutes an abnormal test. Look at this diagram where blue line shows the normal test results and this purple line shows those individuals having the disease. This is one of the idealized graph showing the number of patients with or without a disease, and they are arranged according to their diagnostic test. This test represents that if the test value is lower, it's going to represent a normal individual. Whereas if the test value is higher, it's going to be the individuals having the disease. But you might notice there are some area where there is some overlapping, where it's really hard to distinguish the normal from the ones who have the disease. And in reality, we actually get into such situations where individuals' test results fall on the borderline. In practice, we choose a cut point above which we consider the test to be abnormal, and below which we consider the test to be normal. Consider the following data on patients with suspected hypothyroidism, reported by Goldstein and Mushlin. They measured T4 and TSH value in ambulatory patients with suspected hypothyroidism. The T4 values are given with 5 or less, 5.1 to 7, 7.1 to 9, and 9 or more. Whereas in the next two columns of this table, it shows the frequencies. So there were 18 individuals who were diagnosed as hypothyroid, and their values were in the first class, which is 5 or less, T4 value. Whereas there was only one person which was diagnosed as euthyroid with value less than 5, and similarly we have the whole distribution in front of us. The lower the T4 value, the most likely the patient are to be hypothyroid. So to illustrate how sensitivity and specificity change depending on the choice of T4 value level that defines hypothyroidism. From this table, we make a new table with a new cutoff point with T4 values of 5 or less. And we rearrange this table into a new 2x2 table where one row represents 5 or less, and the other row represents any value that is above 5, which shows that there are 18 individuals who are diagnosed as hypothyroid, and their diagnostic value, T4 values, are less than 5. Whereas there are 14 individuals who are diagnosed as hypothyroid with the diagnostic value even more than 5. So if we calculated the sensitivity and specificity of with this new cut point, you might notice the sensitivity is 0.56 and the specificity is 0.99. Though in this situation, specificity is pretty high, whereas the sensitivity of this test is pretty low. This shows that the test is having a lesser ability to diagnose who are actually having hypothyroidism. Whereas for those who do not have hypothyroidism, test is it's giving like 99% good prediction. Therefore, we try to look at another cutoff value. This cutoff value is set to be as 7. So if this cutoff value, T4 cutoff value, is 7 or less as a first category, and the other categories counted to be more than 7, you see a shift in the values in the cells. And you might notice that sensitivity has increased to 0.78 and specificity to 0.81. Increased sensitivity resulted in some reduction in the specificity of this test. Another cutoff point was chosen where this T4 value is 9 or less, as considered to be those who are hypothyroid, and more than 9 are considered as euthyroid. For here, the sensitivity value is pretty high, which is 91%, and specificity is 0.42, 42%. So you might notice that in all these 3 different cut points, if there is a different value of the cut point, increase in sensitivity resulted in decrease in specificity. So you can make the criterion for the positive test more stricter. There is a trade-off between sensitivity and specificity we have to look after. But let's draw an ROC curve. ROC curve is such a curve that takes false positive rate, which is known as 1 minus specificity on the x-axis, and true positive rate, which is sensitivity, on the y-axis. Drawing this table, you might notice in the second table, we have translated the sensitivity into the true positive, and we also calculated the false positive rate. False positive rate is 1 minus specificity. Therefore, it is 1 minus 0.99 is 0.01, and 1 minus 0.81 is 0.19. 1 minus 0.42 is 0.58. So when you draw the false positive rate and true positives onto the curve, you might notice that this curve is farther away from this diagonal line. If by any chance this curve is closer to the diagonal line, the area under the curve will be less. When we are deciding about the best curve, we look at such a curve which is more closer to the y-axis and having the maximum area under the curve. A diagnostic test having maximum area under the curve is considered to be a relatively better test as compared to the other ones. So it shows a trade-off between sensitivity and specificity. Increase in sensitivity will be accompanied by decrease in specificity. The closer the curve follows the left-hand border, and then the top border of the ROC space, the more accurate the tests will be. The slope of the tangent line at a cut point gives the likelihood ratio for the value of the test. So look at this picture where we are given with 3 different tests and their ROC curves, where one is the blue one, which is kind of very straight. It is far from the y-axis. The purple one, which is relatively better, it's noted as the good one, whereas the yellow one is having the maximum area under the curve. There are a few cut points which are given that if for any test, if area under the curve will be between 0.90 to 1, it will be considered as an excellent test. A test having area under the curve between 0.80 to 0.90, it will be a good test. Whereas a test will fail if the area under the curve is 0.5 to 0.60. ROC analysis is a part of a field called signal detection theory, which was developed during World War II for the analysis of radar image. It was not until 1970s the signal detection theory was recognized as useful for interpreting the medical test results in medicine.